In recent news, researchers at Caltech have taken a monumental step toward developing interstellar light sails, a technology that may soon revolutionize space exploration. This innovation, linked to visionary initiatives like Breakthrough Starshot, is not only a scientific milestone, but a transformative step toward making interstellar travel a reality. In this video, we will delve into three main areas. First, the experimental innovations in light sail design that have produced an ultra-thin, trampoline-like membrane. Second, the precision techniques used to measure the subtle forces of radiation pressure acting on these membranes. And third, the promising future directions, including a surprising discovery regarding light scattering that pave the way for more stable and efficient designs. The breakthrough begins with the innovative design of ultra-thin light sail membranes that might soon power spacecraft to nearby star systems. Researchers at Caltech have crafted a silicon nitride membrane only 50 nanometers thick, establishing a tangible prototype for future light sails. Using advanced electron beam lithography, the team engineered a precise, trampoline-like structure suspended by tiny silicon nitride springs, a design that is as much a feat of modern nanofabrication as it is a key step toward practical interstellar propulsion. In the laboratory, this prototype, a 40-micron square membrane, serves as a controllable model that mimics the dynamics of a free-flying light sail. The miniature system allows scientists to study light-matter interactions at scales that are relevant to real-world applications. For example, by exposing the membrane to laser forces, researchers can gather critical data on how ultralight materials behave under conditions similar to those expected in space. This data is vital for testing theoretical models and refining the design of a light sail that must perform reliably in a vacuum. The use of electron beam lithography ensures that the membrane's thickness and patterning are uniform, which is essential for achieving the consistent mechanical properties needed for light sail performance. The controlled environment of the laboratory minimizes external variables, thereby producing highly reproducible results that confirm the robustness of the design. When a structure as delicate as this membrane can be engineered with such precision, it reinforces the possibility of scaling up to full-scale, free-flying light sails. Moreover, the ingenuity of the design lies in its ability to translate complex theoretical principles into a tangible experimental platform. The membrane's trampoline-like behavior is a practical demonstration of how such structures can harness laser propulsion. When a laser beam strikes the membrane, the resulting force causes measurable vibrations, which provide direct insights into the material's response to radiation pressure, a fundamental parameter for any propulsion system based on light sail technology. This experiment validates the long-held hypothesis that ultra-thin materials can endure and react to the forces necessary for interstellar travel. Researchers can now iterate on the design to enhance performance, stability, and efficiency, all crucial factors for the eventual implementation of light sails in space missions. The development of this platform also exemplifies the synergy between theoretical physics and experimental engineering. A cornerstone of the Caltech research is the precise measurement of the forces exerted by laser light, known as radiation pressure, on the ultra-thin membrane. Scientists have long predicted that radiation pressure, the push generated when photons strike a surface, could be harnessed to accelerate spacecraft to incredible speeds. In this experiment, a visible wavelength argon laser is used to generate force on the membrane, causing it to vibrate like a gently tapped trampoline. These vibrations are not random. They are a measurable response to the laser's push. The experimental setup centers on a common path interferometer, an advanced instrument capable of detecting movements as small as picometers, trillionths of a meter. This level of precision is essential because it distinguishes the minute effects of radiation pressure from other factors like thermal vibrations. For instance, When the laser heats the membrane, it can induce additional motion. However, the interferometer's design ensures that such thermal effects are separated from the pure optical force. The reliability of these measurements is reinforced by a controlled experimental environment. The common path interferometer cancels out external vibrations and environmental noise, ensuring that the data collected reflects only the force of radiation pressure. This setup is significant because it confirms that the observed membrane movements are directly linked to the photon momentum of the laser light, a crucial factor in validating the underlying theory of light-sail propulsion. For example, by calibrating the instrument with known standards, the team has demonstrated that the membrane's vibrations correspond accurately to the expected radiation pressure values. Furthermore, these precision measurements provide insights into the mechanical properties of the membrane itself. The data reveal not only the magnitude of the optical force, but also how the membrane responds to it, including its stiffness and resilience. This diagnostic capability is critical for predicting how a light sail might behave during acceleration or when subjected to varying angles of laser incidence. In essence, these measurements lay the quantitative groundwork needed to design sails that can efficiently convert laser energy into propulsion. The use of such advanced interferometric techniques represents a major technical achievement. By ensuring that environmental noise is minimized, researchers can isolate the signal generated solely by the laser's interaction with the membrane. This precise control is fundamental to advancing light sail technology, as it allows for the optimization of both the membrane design and the laser parameters. In practical terms, the success of this measurement technique supports the feasibility of using light sails for interstellar travel, a concept that has long been the subject of theoretical studies. Additionally, the data clearly indicate that while heating does influence the membrane, the core measurement of radiation pressure remains robust. This separation of effects not only bolsters the confidence in the experimental results, but also guides future modifications to the system. Engineers can now work on mitigating unwanted thermal influences, further refining the measurement accuracy and enhancing the overall performance of the light sail prototype. Looking to the future, the implications of Caltech's research extend far beyond laboratory experiments. The next phase focuses on enhancing light sail stability and efficiency under realistic conditions, challenges that will shape the evolution of interstellar propulsion. Future designs are expected to integrate engineered surfaces that not only harness radiation pressure effectively, but also actively maintain alignment with the laser beam, even in the unpredictable environment of space. Researchers are now investigating how nanoscience and metamaterials can be employed to create self-correcting surfaces. The goal is to design light sails that can autonomously adjust their orientation when the laser is not perfectly perpendicular to the sail. For example, by patterning the surface at the nanoscale, engineers can induce restorative forces, or torques, that realign the sail if it starts to drift off course. This capability is essential because even minor misalignments could drastically reduce propulsion efficiency or lead to instability during acceleration. Current experimental evidence supports the potential of these innovations. Early data indicate that by carefully designing the membrane surface, using tailored patterns and advanced coatings, it is possible to balance the propulsive force with corrective torques. This iterative design process is not only refining the light sail's performance, but also providing a deeper understanding of the interplay between light and matter at extremely small scales. A particularly relevant discovery emerged when researchers experimented with off-axis laser illumination. When the laser beam was angled, simulating the real-world condition of a light sail that is not perfectly aligned, the observed force was noticeably lower than anticipated. Detailed analysis revealed that this reduction was due to edge scattering, a phenomenon where a portion of the laser light is deflected at the sail's boundaries rather than contributing to propulsion. This discovery is critical, as it identifies a key design challenge that must be overcome to achieve maximum efficiency in future light sail systems. The implications of edge scattering are significant. Recognizing that light is lost at the edges, scientists are now exploring strategies to minimize this effect. Possible solutions include designing sails with tapered or specially coated edges that capture more of the incident light, thereby enhancing the net force. This directly informs the engineering of next-generation sails, ensuring that every photon counts when it comes to propelling spacecraft at relativistic speeds. Beyond the technical challenges, this research signifies a paradigm shift in space propulsion. Traditional chemical rockets and ion drives have long been limited by fuel constraints and slow speeds. Laser-driven light sails offer a revolutionary alternative, with the potential to accelerate spacecraft to a significant fraction of the speed of light. This breakthrough could open up entirely new possibilities for exploration, enabling missions to nearby star systems that were once considered purely the realm of science fiction. Thank you for watching and joining us on this journey through the cutting-edge science of interstellar light sails. Stay curious, keep exploring, and we'll see you in the next video.